Hello everyone and welcome back to Not Only Math. Thank you so much for joining us here today as we continue our discussion of linear functions. So far we've already looked at 2 or 3 different types of problems that result in linear patterns or patterns that can be modeled using a linear function. We took a day and talked about just some very simple word problems. We took a day and talked about some geometric growth patterns, and then we took a day and talked about arithmetic sequences. Today our focus is not so much going to be on the different types of problems that result in linear patterns, but rather in different ways we can represent or show those different patterns. So what I'm going to do is I'm going to give you a problem very similar to one you might have seen a couple days ago. It says this: Rosalind babysits to earn extra money. She charges $8 for the first hour and $3 per hour after that. Now this is a linear pattern because it has both a starting point and a constant rate of change, which we typically would model using the equation y equals mx plus b, where m is the constant rate of change and b is the starting point. For those of you that don't know, Rosalind is the babysitter in the famous comic strip by Bill Watterson, Calvin and Hobbes. So shout out to Mr. Watterson there for his creative genius. What we're going to do, though, is we're going to take this situation, this story, and we're going to model it using a table. We have 2 methods shown here for modeling that type of problem. We have the word problem itself, and now we're going to talk about a second way to represent that, and that is the table. Before we can do the table, though, we need to think about what the independent and dependent variables in this problem might be. In other words, when I look at this scenario, it is impossible for me to know how much money Rosalind has earned without knowing how many hours she has worked. There's 2 unknowns here. There's the amount of money and there's the number of hours that she works. One of those is dependent on the other. Do you know which one it is? Hopefully you've realized that the amount of money she earns is dependent on the number of hours she works. So if she only works for 1 hour, she earns $8. If she works for 2 hours, she earns a different amount, but it is conditional. Remember that the independent variable is typically described in our pattern as x, and the dependent variable is typically described in our pattern as f of x or as y. So let's use this table to model what we think will happen in the situation. It says she charges $8 for the first hour. So 1 hour is $8. Notice I skipped over this 0 row. Be very, very careful and conscientious about where you put that value because she doesn't earn $8 for 0 hours. She earns $8 if she works 1. And then we know she earns $3 per hour after that. So if she works 2 hours, she would earn 11. If she works 3 hours, she would earn $14. And we said in our previous video that we can use this number here, this constant rate of change, to help us predict what that pattern is going to be. We also, however, need to know what she would get paid if she worked 0 hours. So we take that plus 3 and work backwards. 8 plus 3 is 11, 11 plus 3 is 14. Or in reverse, 14 take away the 3 puts us at 11, 11 take away the 3 puts us at 8, 8 take away 3 puts us at 5. So now we have both a constant rate of change and we have a starting value of 5. So we can write this pattern as y equals 3x plus 5. Or if I want to color code it so it matches my pattern up here, y equals 3 is your constant rate of change, 5 is your starting point. If I want to put it in function form, I would say it is g of x equals 3 times x plus 5. These both mean the same thing. This is just equation notation. This is function notation. Usually we use f of x, but I threw in a g of x just to be creative and to let you know it really doesn't matter what we put. Now, just for the sake of making sure I clear up any issues people might have, students often ask me about this 5 and they say, Mr. Nelly, it doesn't make any sense for her to earn $5 if she works 0 hours. And you are probably correct. We have to think of this not as being $5 for 0 hours, but rather as an initial charge of $5. If she's going to work 1 hour, she's going to charge that initial $5 plus $3 for the hour. If she works 2 hours, she's going to charge an initial fee of $5 plus $3 twice, once for each hour. This 5, even though she wouldn't charge $5 for 0 hours, is a fee that isn't on top of her normal hourly rate. So when I see this equation, I think of the $3 as being an hourly charge, and maybe the $5 just being a extra cost for budgeting my time to come visit your house to babysit. Or maybe I charge you $5 just to come, and then I charge you the cost per hour. A lot of different ways to think about this. What I usually tell my algebra students is this. A lot of times when we create a linear function, the linear function has a limit to when it will apply. For example, our function, we could limit this function, say, this rule will work for 1 hour or more. Or maybe if she works 10 hours, she doesn't charge this amount anymore, maybe she charges something else. It's called a limit on the domain of the function. Or in other words, we just say this is only true for certain values, but may not make sense at 0 hours. Additionally, you might have to say, you know what, we wouldn't work negative hours, and if we work enough negative hours, we wouldn't pay them refunds. And you can kind of think of it that way. Hopefully that makes you feel a little bit better about this particular pattern. Now, what I'm going to do is I'm going to create a graph of this story. The graph of a function is our third representation. Actually, let me rephrase that. That is our fourth representation. You have the word problem, that's 1. The table that you have here, that's 2. The equation or function is 3. The graph is the fourth way we would represent this. Now, when we draw a graph, it's important for us to remember that the x-axis is the horizontal axis, and the y-axis is the vertical axis. Remember, that means all of our x values, or our hours, or our independent values, will go along x, and our dependent values, or in this case, our dollars, will go on y. So when I say x, or independent, or hours, that's all the same thing, and it's dictated as right and left motion. Dollars, or y, or dependent all mean the same thing, and those are all going to be indicated on our vertical axis. So when I say if she works 0 hours, she earns $5, I would just represent that as a dot on that y-axis. Notice I've gone over 0 hours and up $5. She gets $5 just for arriving. The coordinate 1, 8 says if she works 1 hour, that's over 1, she gets $8. 2, 11 says if she works 2 hours, that's over, she gets $11, that's up. 3 would be 3 hours, $14, that's over and up. And we can continue that pattern on and on. Remember, just because I run out of room on my graph doesn't mean that she stops earning money. It just means that I don't have room to show every single possible value. Now, since I can't show every single possible value, I'm going to draw a line through those dots showing what the pattern is. When we graph a linear function, every point or every dot on this line represents a possible combination of hours and dollars. So even though I couldn't do 1, 2, 3, 4, even though I didn't have 5 hours in my table, I can look at this and see if I count up over 5 hours, this is up $17. I could go over to 6 hours and go up to the next dollar. I can continue that pattern on and on. Likewise, you'll notice that I could have her only work half an hour. And if she works half an hour, she would end up right here. That's $6.50. Up $3 every hour would be up $1.50 in half an hour. This is the graph of this story. Now, if I had been extra careful and conscientious about this, I probably should have put a title on this graph as well. I neglected to do that, but just be aware that graphs with stories attached to them typically will have titles. Now, I want us to think for just a second about this rate of change, this 3 over here, because we've used the term rate of change in a different unit. Do you remember when that came up? We talked a lot about the rate of change when we were doing our proportions unit or our ratios and proportions unit, because we said the rate of change is a specific ratio. It's the ratio of how Y changes, or how dollars in this case changes, compared to how X changes, or hours. This rate of change says how much does the money change when the hours change. Or in the case of this problem, the dollars are going to rise as the hours run. Do you remember that ratio, rise over run? We're looking at how much the dollars change when the hours change. Well, take a look here. I'm going to rise $3 every time I run $1. Rise 3, run 1. Rise 3, run 1. Rise 3, run 1. That is the slope of our line. There's another term we've seen before back in our ratios and proportions unit. The slope is the ratio between how much your graph rises and your graph runs. You see, slope and constant rate of change are the exact same thing. And in this problem, they're both $3 per hour. This number right here tells you how fast your graph is going to go up. It rises 3 every time it runs 1. This number right here is the same as our slope. Likewise, if you look at where we cross the y-axis, that's known as the y-intercept, you have the coordinate 0, 5. Notice that when you have 0 hours, you get $5. That's the same as this number right here, this 5. In fact, your slope will be the same as your constant rate of change. Your y-intercept will be the same as your starting point or initial value. And because of that, we often refer to y equals mx plus b as the slope-intercept form of a linear equation. M is the slope. The slope is the steepness of your line. The slope is your constant rate of growth. B is your y-intercept. Y-intercept is another name for your starting value or your starting value. This pattern right here, I put it in a box. You're going to want to star it, highlight it, circle it. This pattern right here comes up a lot in higher mathematics, beginning in Algebra 1. You're going to see this quite a bit in Algebra 1, and it's going to continue on into other courses. That's one of the reasons why we spend so much time developing what it means. Whew. That's a lot, isn't it? Tell you what, let's do another one. We're going to do this one just a little bit faster this time. Here's your story. A snake is 3 inches long and it grows ½ an inch per week. That's our first representation. That is the word problem representation of this story. So, in order for me to work with this, I need to know what my independent and dependent variables are. I would suggest you pause the video, write down what you think they are, and then watch me do it so we can see if we're on the same page. Well, let's see. There's two things going on here. We have a number of weeks that pass, and we have how long the snake is. Which one depends on which? Does time depend on how the snake grows? If the snake doesn't grow, does time not pass? Well, that doesn't make any sense. But the problem says as time passes, we can use that to predict the length of the snake. So time is independent, it's weeks. The snake's length is dependent. So when I set up my table, I'm going to do my snake's length as y, or f of x, and I'm going to have time be x. In this story, we know the snake is already 3 inches long. That's before we start counting. Notice this time in my table, my 3 goes next to the 0. In the last problem, the value that was given was next to the 1. It's very common for students not to be careful about where that first value goes, and it causes them to have some errors. But for us, the snake starts off at 3. After a week, it's ½ an inch longer, so it's 3½ inches. 2 weeks, it's 4 inches. 3 weeks, it's 4½ inches. Notice you have a constant rate of change here, and you have a starting value. The starting value is where you are at 0. you could use those two numbers to give the slope-intercept form of that equation. Y equals 1/2 x plus 3. Notice 1/2 is just the fraction form of 0.5, and 3 is our starting value. Or, as an equation, y equals half of x starting at 3. As a function, I just put h of x this time equals half of x plus 3. Notice I said f of x up here. It doesn't really matter. I probably should have been more careful and made those match. I think I'll go back and change that in my notes, but just be aware that f of x, g of x, h of x, they're all ways of describing a rule in function form. If this makes you uncomfortable, you'll notice that I have left out the middle column on our table that I was using in previous videos. You might want to draw that middle column for your own tables if you're drawing your own. That may help you with walking through this process. I think most of my students at this point are probably at the point where they can see the constant rate of change, they can see the starting point, and they can generate this probably without ever drawing the table. Ideally, we'd like to get to that point where we see the word problem and we can jump straight to the function without having to walk through this middle step. Either way, when I go to graph this, remember x is my horizontal axis, y is my vertical axis. That means my independent variable is going to go across. My dependent variable is going to go up and down. So in this case, weeks is side to side, inches is up and down. So at 0 weeks, my snake should be 3 inches long. At 1 week, it should be 3.5. At 2 weeks, it should be 4 inches. Now, I'm going to pause here and point something out to you just really quickly, and that's this. Did you notice that going up a half over 1 is uncomfortable or inconvenient? A lot of my students don't like that, but I want to show you something cool. Up a half over 1, this slope is the same as up 1 over 2, a rise of 1 and a run of 2. So if you don't like going up a half every time, you could use rise and run and rise 1 over 2, rise 1 more over 2, rise 1 over 2, rise 1 over 2. And you can continue that pattern till you run out of room, and then draw your line through those points. And that's going to show how the snake grows over time. There again, I don't think it's terribly difficult. Keep in mind that slope is rise and run. So if I'm rising a ½ inch every week, when I divide that, that is ½ inch per week. ½ inch per week, which does match the slope here. The rate of change and the slope are the same thing. Also notice that your y-intercept is where you cross the y-axis, 0, 3. That's also the same as this value, your starting point. Starting point and y-intercept mean the exact same thing. Here's another problem I'd like you to try. Mr. Nunley has $15 and spends $2 per day. I want to model this situation with a linear equation. Now I'm going to recommend that you pause the video and you try and do this on your own before watching me do it. I am going to start doing these a little bit faster because you ought to be getting better and better at them. In this story, the first thing you're going to want to do is you're going to want to figure out what your independent and dependent variables are. Then try to write the equation, then go through and draw your graph. Don't make a table this time. Let's see if we can do this without the table. In this story, you have two things that you don't know. You don't know how many days have passed, and you don't know how much money Mr. Nunley has. What you do know is the amount of money depends on the days. As time passes, more money is being spent. Typically, time will be our independent variable because we don't have a whole lot of control over time passing. Rather, whatever we do happens or occurs as time goes on without our control. So whatever else is occurring typically is going to be dependent. In this problem, I know that I'm spending $2 per day. That is my constant rate of change, or in the case of my graph, it's going to be my slope, and it's given to me right here. I know this is the rate of change because this is what's happening repeatedly. I can see this phrase every day or per day. That tells me that this is the repeated addition or subtraction. And that means that my starting point was the $15. So if I wanted to write my equation for this, I would take my slope-intercept pattern over here at the right, and I would just plug in my slope and my y-intercept. Y equals negative 2x plus 15. There's our equation. When I go to graph this, again, the independent variable, or time, is going to go across the x-axis, the horizontal axis, and the y-axis is going to be vertical. That is my dependent variable. So independent is horizontal, dependent is vertical. In this case, time in days is independent, amount of money in dollars is dependent, and then I'm just going to start plugging in values. At 0 days, I have $15. My rate of change says I'm going to go down $2 every day, so down 2 over 1. And I'm just going to keep doing that. Down 2 over 1, 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 and so on until I can draw my pattern. Again, I like to use lots of dots because it helps me keep my graph from going crooked or going off where I intend it to go. You'd be surprised how easy it is, even with a ruler or a straight edge, to draw that in an incorrect manner. And there's your graph. A couple things to point out. Remember, even in between these dots, there are possible values that would work in this equation. If 1.5 days pass, I could get a value between these two values. Also notice I didn't draw an arrow over here. I don't think that going into negative time makes a whole lot of sense. And over here I did kind of stop at my x-axis because going below x into negative dollars may or may not make sense in this story as well. We'll get deeper into that in a later video. Once we know the pattern, we see the graph, I can begin to ask you questions about that pattern. How much will Mr. Nunley have left in 5 days? Two ways to approach that. Method number one, I should be able to look at my graph and go over 1, 2, 3, 4, 5 days and go up and see how much money is left. This is the coordinate 5, 5. In 5 days, I should have $5 left. I can see that quickly from the graph. The other way to do that is to take the rule we created and just plug 5 days in as my time and compute it. And it comes out as $5. Notice that my result from my equation should match the result from my graph. Likewise, I could ask you the question, after how many days will Mr. Nunley have $7? Again, I can go over to my graph and say 1, 2, 3, 4, 5, 6, 7. If this is $7, I can look and say, well, I have $7 left after, let's see, 1, 2, 3, going over 4. In 4 days, I would have $7. Or, again, I could take the function, plug 7 in for dollars, and then use our equation solving skills to figure that out. Subtract 15 from both sides, divide both sides by -2, and you end up with 4 days. Now we have multiple methods to solve the problem, either looking at the graph or using our equation and our algebra rules. The third method, which we did not do here, would have been to look at the table, but we didn't bother to create that, so that's not going to help us in this scenario. Here's one more opportunity for you to try that. Let's read this together. Miss Osterwish spends about 2.5 hours per lesson creating online resources. She's already spent 6 hours doing other schoolwork this week. How much time does she spend working? We're going to, again, define an independent and dependent variable. Then we're going to create the equation. Then we're going to create the graph and then answer some questions about it. I would recommend that after you define your independent and dependent variables, you pause the video before going on and watch what I have to say. Or I should say restart the video and watch what I have to say about that before you move on, just to make sure you didn't make a careless mistake. I think this one's just a little bit tricky because in this problem, notice that your time is what's dependent. That's extremely unusual. Typically, time causes other things to happen. But if you look at this problem, we're trying to figure out how much time was spent working. Well, how much time did she spend working depends on how many lessons she made. If she spends 2.5 hours on every lesson, we're going to be counting the time based on how many lessons she has done. That's the opposite of what we would normally see. In this case, it's 2.5 hours per lesson, and she's already spent 6 hours on the problem. One little shortcut for knowing which one's independent and dependent is if you look here and it says hours per lesson, You'll remember that our slope is always rise over run. And in this case, the rise, or y, is going to be ours. Little trick there for figuring that out. Remember, slope is change in y over change in x. So if you get a phrase like hours per lesson, where you have that per in the middle, you can pick up your dependent and independent pretty quickly. Well, once you know those two things, that's really the hardest part, because you can plug those values into your slope-intercept equation, and then you just start to graph. Notice again, x is horizontal, y is vertical, independence horizontal, dependence vertical. In this case, the lesson is horizontal and the hours are vertical. That's very unusual. It still messes with my brain a little bit. And then I just start plotting points. It says I'm going to, where's my cursor at? It says I'm going to start, oops, there I am. Okay, I'm going to start at 6 hours. And then every time she does a lesson, she's going to go up 2.5, up 2.5, up 2.5, up 2.5. Notice once I was up 2.5 and 2.5, I end up here. That is up 5 over 2. Remember, 2.5 as an improper fraction is 5 halves. You may find it easier to put these in improper fraction form rather than to use mixed numbers. Up 5 over 2, up 5 over 2, and you get a graph that looks like this. If I ask you if she needs to prepare 10 lessons this week, how many hours would she expect to work? Notice we're trying to figure out the number of hours. Hours is our y. That means that the 10 goes into our equation for x. And we just use computation to calculate that. Likewise, how many lessons can she get planned if she works for 25 hours? In this case, we're given hours. Remember, hours is y. We plug that in and we solve for x using our algebraic equation solving skills. To get rid of a plus 6, we do minus 6 on both sides. To get rid of a times 2.5, we divide both sides by 2.5. And you get about 7.6 lessons. Also, if my graph were bigger and I could see beyond just the space of what we've drawn here, we could find those values by looking at the graph. The problem is that if we're talking about 10 lessons is going to be over 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's going to be something way, way up here on our graph, which we didn't draw. That's one of the shortcomings of looking at graphs, is if you get really big or really small numbers, sometimes they're hard to read. Hopefully this has been very helpful and useful for you. As always, I do appreciate you taking the time to watch. Make sure that if you got something valuable out of this, that you give us a big thumbs up. Make sure that you hit that bell, ring that bell, so that you receive notifications when new material comes out, because we're going to have a lot of cool new stuff coming out of Nunley Math. As always, thank you so much for joining us here today. I do wish you all the very, very best. Take care of yourselves. Bye-bye.